mode.
Good evening and welcome to our webinar tonight. We appreciate you joining us for part one of Statistics for Physicians. Just a few housekeeping items before I introduce our Executive Director, Dr. Orient, to introduce our speaker. First of all, I just want to make sure everyone can hear me. If you can hear me, if you could, a few of you just click the hand icon on your control panel just so I can see that a few of you can hear me. Okay, great. Thank you. Thank you for doing that. All right. I see hands coming up. All right. So just a few other quick announcements. At the end, we'll have a Q&A period. And there's a couple ways to ask questions. One is you can type your question into the question/chat window, and we'll get to your question at the end. And the other way, if you'd like to ask your question verbally, you can type or you can click your hand button to raise your hand, and then we'll call on you and unmute you at the appropriate time. Now, just a couple other announcements. One is about the post-meeting evaluation. At the end, we'll give you a link to fill out an evaluation, and once you've filled that out, you'll get another link to download your CME certificate for tonight. And also just a quick reminder about part two, which will be next week at the same time. So if you haven't yet registered for that, we'd love to have you join us for next week's presentation, and you can find that registration link on the AAPS website. So with that, I'll introduce our Executive Director, Dr. Jane Orient, who will introduce our speaker. Dr. Orient.
Well, thank you all for coming. This is a new experiment by AAPS in having CME for clinical topics. I think that the topic of statistics is one that we are perhaps not exposed to very often, but in the age of evidence-based medicine, if we want to be able to evaluate the evidence for ourselves instead of just trusting and parroting the gurus, then we need to have some of this basic understanding. We were absolutely delighted to have with us Dr. Herman Bork, who comes to us from the University of North Carolina. He was trained at Yale University. His specialty is neuroendocrinology. He has designed and led numerous research projects, including clinical investigations, basic research, and animal studies, and is extremely well qualified to talk to us about the understanding of both statistical description and inference. Dr. Borg.
Thank you so very much. And we'll start with the presentation of the educational objective from the study, and the slide is coming in a second. The educational objective of this lecture are to define statistics, to discuss the significance of statistics for physicians, to suggest the study strategies for learning statistics, present role of statistics in the scientific process, and review basic concept of statistics. Finally, we'll introduce methods of exploratory data analysis, and this will continue during the next lecture. We'll start this lecture with a few of introductory quotes. The importance of statistics for physicians is underscored by the following statements. First statement, right here, was made by the physician scientist Dr. Altman in his paper entitled "The Scandal of Poor Medical Research." Dr. Altman wrote, "Amazingly, it is widely considered acceptable for medical researchers to be ignorant of statistics. Many are not ashamed, and some even proud, to admit they don't know anything about statistics." A sad state of affairs indeed, as seen from the perspective of medical science. The second statement comes from the Internet Journal of Healthcare Administration. I apologize, the second statement comes from the Journal of Healthcare Administration, and it was made by Dr. Singh, who stated, "It may not be expected for doctors." I'm sorry, I'm just having this problem with jitterness, and it's going to fix in a second. Okay, we're back. "It may be not expected from doctors to be experts in statistics, but they should be made capable of understanding the basics of statistical methodology." So this is a perspective, as we can see, quite demanding one from the healthcare and business administration perspective, as they always are quite demanding. And the final statement that sums it all up was made by Dr. Chang, a statistician who teaches statistics to medical students. "Medical students may not like statistics, but as good doctors, they will have to understand it." And this is simply a statement made from the perspective of a common sense. So let us start from defining the subjects. Statistics is defined as both theory and methodology for the collection, organization, analysis, interpretation, and presentation of data. Statistics have two main branches, namely descriptive and inferential. Descriptive statistics is a discipline of quantitatively describing the features of data, while inferential statistics deals with drawing conclusions from the datasets. Familiarity with statistics gives any physician ability to understand, number one, the value of published medical research, and number two, the role of statistics in medical business and in the business of administration of medical business. And this feature appears to be much more important recently than ever. We will start with discussion of role of statistics in medical research. Well, as seen on this cartoon here, without statistics, the laboratory mice would have nothing to do, and they would get bored. Well, it's very sad, but seriously speaking, in the past, the use of statistics, the proper use of statistics in research was its most significant aspects. And this was not so remote past. Unfortunately, today, the misuse, inappropriate use of statistics in research became a major concern. And I depicted here on the left side of the slides two major offenders, which are media as well as groups that have a vested financial interest in the outcome of research. But let's talk about a proper use of statistics in science. Statistics is an essential aspect of modern science, and one can argue that without statistics, modern science would not exist. Indeed, before statistics, the science was perceived as the process of developing absolute knowledge through observation. In a contrast, statistics is based on the notion that scientific knowledge is not absolute. Hence, uncertainty and error are part of science. The only real thing in science is the distribution of numbers. Then probability theory is used to interpret those distributions. Therefore, statistics and, in turn, the science reflect acts of interpretation, not irrefutable facts or dogmas. The modern science is tentative. It is probabilistic. And every scientific statement in the modern world will remain tentative forever. So this was a lofty view of the statistics from the academic perspective. And now a little bit of a dirty practice. For your entertainment and amusement, I just compiled the list of the statistical terms, or if you wish, a jargon, from the 6 original contributing papers published in JMA. Now, some of those terms sound familiar to most of us, but some are absolutely exotic. And the situation is even worse when we understand that those are just 6 papers, and those exotic names are not just a jargon which is meant to obfuscate and obscure one's intention, but those are actually very complex and sophisticated mathematical instruments that have a specific goals of helping in answering an important research question. But now let's turn into misuse of statistics, and the major offender in this era are media. Unfortunately, in developed countries, much of what laymen know about medical knowledge is gleaned from the media. The more frightening the event is, the more horrible, the more danger is included in it, the more newsworthy it is. Therefore, the statistical analysis, which is complex, is very frequently oversimplified and very frequently sensationalized in order to get the results, which is high ratings. And I depicted this state in the little picture on the left. We do not longer have a Newsweeks. We have a Newsfears weekly with emphasis on fears. That cartoon summarized the history and the current state of media role in reporting scientific news and interpreting statistics quite well. The random medical news from the New England Journal of panic-inducing gobbledygook. Indeed, take any random thing, say that it caused that or that or that, and then we have an anchor who is telling frightening audience what researchers just uncover. Now, that was all bad. However, there is even more sinister way in which statistics is misused. It is being used to advance hidden agendas, and most of those hidden agendas are of a financial nature. And the schematics of those plots are shown here. First, the research, quote-unquote research, is commissioned, and we have here a diligent scientist who is reading How to Lie with Statistics handbooks. The next step is publication of quote-unquote results, and what we have is an instant sales booster for the master who paid for said research. So there is no question that statistics can and is misused. And I give you a famous statement made by Mark Twain. There are lies, damned lies, and statistics. So very true. Indeed, data dredging, data fishing, data snooping, and my favorite term, equation fitting, is the inappropriate use of statistics to uncover misleading relationships. Having said all of that, we shall remember that statistics don't lie, but liars use statistics. Statistics is an innocent tool that can be horribly and is misused. And that brings us to importance of keeping things simple in research in general and in statistics in particular. The simplest form of statistics will suffice in most well-designed studies. Therefore, a revision of the study design should occur before the use of more sophisticated analysis. Similarly, any study that uses overly complex statistical methodology should be approached with caution. This emphasizes the importance of knowing the basic of statistics. If you see some test that appears to be exotic to you after you have studied the subject very carefully, there is something strange going on there. Let us turn into the role of statistics in medical business. And the little graph presented here on the right side says it all. We have the all-seeing eye of a business administrator who is overlooking and managing the following process. The process starts innocently enough with a doctor consultation when doctors see patients face to face. What follows is obviously note writing, prescription writing, test ordering. And that translates to the fact of clinician and his staff recording the data and entering this into the computerized database, where the data is first stored. Subsequently, they are subjected to so-called data mining process, which is followed by the knowledge discovery part, and that results in the generation of reports that are statistical analysis, and the statistical analysis come back to clinician and indirectly to the patient, because clinician is supposed to follow what the report says. And it's a good thing if this is improving the quality of care, but it can be bad thing if the statistics is misused. So let's spell out the significance of statistics in the modern medical business. This is something that I have learned from my mentor here at UNC. As opposed to the past, we now live in the quantitative era. It is not apparent outwardly for us, but it is. In clinical environment, everything is measured, and measured strictly. All aspects of physician work is being statistically analyzed and compared to benchmarks such as evidence-based guidelines, idealized peers, etc. And as my mentor stated, any physician who does not understand this will be crushed, indeed. So, to some extent, the vision of Fritz Lang's metropolis has realized right now in the clinical world. And how this has happened and how this is possible. One of things that facilitated it is computerization of medical business, because computerization facilitates automated surreptitious data gathering, data mining process, performance of physician performance analysis, outcome and cost effectiveness analysis, practitioner versus peer group comparison analysis, and finally more accurate actuarial analysis, that is estimation of risk in the future based upon the past. And all those things can be good or could be bad depending what the agenda of the entity performing such operation is. So I believe that we are all convinced right now that statistics is extremely important for vast majority of physicians. Yet it is very challenging to study the subject. Most physicians dread studying statistics. Statistics is challenging for everybody, but physicians might find it especially challenging as statistics is math-based. It has many rigorous quantitative aspects rooted in mathematics, and most physicians are not used to study math-based subjects. I mean, we have an exception, colleagues who really should be engineers or mathematicians, but those are not very common. Statistics is time-consuming. It's a tedious subject requiring a tremendous time commitment. And who has it, especially today? Finally, statistics is spuriously not essential. It appears to be not everyday topic. Physicians deal with so many practical clinical issues and with so many billing issues, and those in academia with so many organizational issues that we don't really see it. Even researchers are concentrated mainly on the performance of experiments that could be challenging. Epidemiologists are concentrated on collecting the data, and it appears to be, well, I can really get away with this. Not really. So that brings us to the topic which is omitted in the formal lectures, even for physicians and medical students, how to effectively study statistics. The first realization that has to come in mind is that statistics is not a spectator sport, but it is a sport. It's more than microbiology and pathology or even neuroendocrinology, with all due respect for those very fine sciences. Statistics is a sport, so one shall get motivated first by understanding why one needs statistics. As not spectator sport, one cannot just sit and watch. One has to learn statistics actively. It cannot be crammed. In order to study it properly, you should always use pen and paper for solving problems and reflecting on ideas when studying the textbook. One has to make her or his own scenarios testing the concepts. Definitely, as you can see, as much as I'm doing my best to convey information to you, you have to do it on your own. It's just a start. One has to study deliberately, as few words and symbols can mean a lot in statistics. There are certain medical sciences where it's true as well. However, statistics is very peculiar in the sense that the one symbol or one number can mean a lot. In addition, the statistical concepts are sometimes very counterintuitive and confusing, and it may be necessary to read a topic many times. Statistics required a steady effort. One could say, well, but most of subjects do, but not really. I mean, you can really try to cram anatomy in one night if you really press to. But statistics is not similar to anatomy at all. It has to be studied incrementally. It is based on a small number of principles, and those principles are sometimes counterintuitive and not really easy to infer from other principles. So those basic principles must be memorized and understood first. It is futile to look up the advanced tests such as used in research paper without knowing those essentials. This is like trying to study the paper in the foreign language without knowing the vocabulary. Also, one has to assemble resources. And many of us have a favorite pharmacology textbook or one favorite internal medicine textbook or one favorite surgical textbook, but this is not true for statistics. There's no single best statistical manual because of its very nature. So it pays to prepare a set of personal references that will include several sources. After this introduction, let's turn into the role of statistics in the scientific process. I'm presenting to you two views on the role of scientists and of the statistics and the scientific process. One, depicted on the left by the University of Oxford, England, and the second, simplified view as presented by the LISA, which is Laboratory for Interdisciplinary Statistical Analysis at Virginia Tech, an American version. A little shorter and a little more elegant, but generally speaking, the meaning of those two pictures are the same. A statistic is omnipresent, which is not palpable for a researcher, and it's even less palpable for a physician who is reading the scientific paper. The statistics occur at the level of formulating a hypothesis and really is essential and crucial on the end. So it's pretty much saturated the whole process. As I stated before, in order to apprise in a proper critical way any statistical document such as research paper or a business analysis, one should understand the concept of statistics that are basics. And this is what we are going to do next. Let's start from the absolute basics. Population versus sample. Population are all elements to be studied. Population is characterized by parameters. Parameter is a characteristic of a population. An example of parameters include mean, standard deviation, and so on, the indices which we are going to discuss. In a contrast to it, a sample is a subset of population. And equivalent to parameter for sample is statistic. Now we have an example of statistical jargon. The thing that characterizes a sample is called statistics. A statistic, very confusing. It has no S on the end, but has nothing to do with the major science of statistics. So sample is being characterized by statistic that is characterization of the sample, which is the same as for population, except is limited to the subset of it. Another basic terms, variables. Variable is any measurable attribute that differs in the course of observation. Variables could be divided into two major groups, namely quantitative, numerical, that represent numbers, and qualitative or categorical that represent categories, but they are not numbers. Quantitative and numerical variables are then divided into continuous. Those are variables that can take any value between a set of numbers. And great examples are time, weight, and so on. Discrete numerical variables are those who can take only finite number of values. A great example is the number of children in a family. One can have 1, 2, 3, but never 5.6 children. Quantitative categorical variables can be divided into ordinal that can be ordered in certain order, hence the name ordinal. They can be ranked. For instance, clothing size can be ranked from small, medium, large to extra large. Nominal cannot be ordered or ranked in logical fashion. And examples here are colors. We may have one favorite colors or a few more, but it's very difficult to put colors in the order. The term data and variables are being confused, and rightfully so, because they are actually the same. Data are values that variable can assume. Consequently, just like variables, data can be numeric, categorical, and respectively continuous or discrete, or ordinal or nominal. Data analysis can be univariate, that is, analysis of one variable, bivariate, analysis of two variables, or multivariate, when analysis of many variables is occurring. Now let's talk of the extremely important aspect of statistical analysis. Its phases. As I mentioned before, there are numerous phases of a research process in which statistical analysis occurs. And those phases correspond to the phases of statistical analysis. And those include, number 1, sample selection and data collection. Number 2, process known as initial data manipulation, cleaning of the data that includes data formatting and data quality control. This is followed by exploratory data analysis that includes tabular, numerical, graphical data summaries to have a better outlook on the data set available. And then it includes choosing the way of definite analysis. Definite data analysis is a final interpretation and inferential conclusion that are drawn from the data set that has been prepared by the previous processes. And finally, we have presentation of conclusion, which is a concise, graphical, and tabular summarization of the data and statement of conclusions. Now, let me emphasize the significance of understanding of the phases of statistical analysis. Understanding of those phases are important not only for those who perform research. It is essential for the critical appraisals of all published studies, and this truth is frequently overlooked. Because it appears logically that when we have either a scientific paper or when we have a business analysis in our hand, all what we can see is a presentation of conclusions. But this is not true. One can and actually shall read between the lines and see how the other phases went in order to arrive into the presentation of conclusion. And this is very telling. Presentation of conclusion can be very clean up and can be very misleading. Yet, in the good business analysis and in the good scientific paper, one can read very well between the lines regarding how well or how bad or how poorly the other phases of statistical analysis were performed. Therefore, in those two lectures, we'll go step by step through each phase and part of the process of data analysis. Sample selection and data collection. That's what most researchers are focused on, especially medical ones think that this is all what entails in research, and then you take a bunch of data, give a statistician, and then you're going to have results, and very bad attitude. Yet, sample selection and data collection are absolutely critical for the results. The goals of sample selection and data collection may be both descriptive, that is, describe a population using information from a sample, and finally, the goal is an analytical inference that is described relationship between variables using a sample, assuming that it can be generalized to a population. Yet, it is very clear here that descriptive inference is critical for analytical inference, because if data are collected in the wrong way, the collection process, which is executed poorly, can have a tremendous impact on the conclusion. Sampling. Sampling process appears to be a very simple matter, but actually there are numerous types of it, and I listed just a few of the most popular ones. It could be a simple random sampling, stratified sampling, clustered sampling, and multi-stage sampling. Simple random sample is the most commonly used and the simplest methods. It can be compared here to the just drawing from the hat. Subset of individuals are chosen randomly from population. Each individual, therefore, has the same probability of being chosen. As simple as this method is, it is not always feasible, but sometimes it can actually obfuscate the research question. And therefore, the stratified sampling should be applied. Strata are homogeneous, non-overlapping subgroups which happen, but they are not happening in natural fashion. They are rather, as it showed on the left side in the picture here, are mixed in the whole population. So the stratification process has to be applied, which is dividing population into the strata. And good example are gender or race. So if we have, let's say, a population of a Yale University, then we can divide it into the population of subpopulations of male and female students or students who have different races. Stratified sample is obtained by sampling. We're using this random sampling methodology from each strata, as it's shown on the left in the picture. Clustering and cluster sample. That's very frequently confused with strata, but it shouldn't be because the concept is different. Clusters are naturally occurring heterogeneous subgroups that are representative of population. So they are occurring, but one does not really need to make them, like in the stratification method, but they are present and they are available to be taken advantage of in the statistical work. A picture on the left shows that we have a population, but the population has a naturally occurring cluster in it. If we use the example of Yale University, then Yale University is a population, and its colleges, such as, for instance, Vanderbilt and Davenport colleges, are clusters. The clusters are believed to be a reflection of population, so that simplifies the sampling process. And cluster sample is a sample obtained by simple random sampling of each cluster. Now this all is fine and dandy and sound easy, but when we go to the little more complex and sophisticated studies, especially long clinical trials or epidemiological studies, this is not very simple. And a combination of methodologies should be applied, such as multi-stage sampling. It is a form of cluster sampling. When using all the samples element in the clusters, it's undoable. Then instead of doing this incredible, sometimes simply physically impossible work, the researcher randomly selects elements from clusters, as it depicted on the picture on the left. And this is very counterintuitive sometimes, and it's really difficult to find a good illustration to do it. But basically speaking, imagine that we are not dealing with a Yale University now, but we're dealing with a population of all universities around the world, and we would like to perform statistical analysis there, and we're simply not at the liberty to use a clustering for all the thousands of colleges there. So let us talk about initial data manipulation, the next phase of the statistical analysis process. And the picture on the left here presents very nicely what initial data manipulation is. It's a cleaning of the data, in the good fashion, of course. Initial data manipulation is putting a data set into order, making it usable. And it includes data formatting, because initially we just have a bunch of numbers which are all over the place, and we try to format it, putting in some order. The next step is checking quality of the data, especially looking for outliers, checking implementation of design, and developing a basic characteristic of the data, which brings us to another terminology which is frequently right now used, term outliers. Outliers are data points that deviate remarkably from the majority of sample. Initial data analysis requires the knowledge and understanding of the concept of distribution. We are going to discuss distribution in great details during the next lecture. However, the initial data analysis required basic knowledge about the distribution of data as the data are being cleaned and put into the order. Distribution is the pattern of occurrence of the various values and of variable. So distribution is a pattern. Population distribution is a distribution of values all units in the whole population, an abstract thing that is very rarely possible to be observed. Empirical distribution, on the other hand, is a distribution of values for the units in the sample, and it is easy to done provided you have a small sample. It is assumed that the empirical distribution is a good representation of a population distribution. So what is practically a distribution of a data set? It is a listing or function showing all the possible values of the data and how often they occur. Distribution of categorical data shows the number and percentage of individuals in each group as it depicted in the left upper corner. There's a simple table that just shows that. Distribution of numerical data is typically presented using graphs and charts and tables as well to examine the shape, the center, and the amount of variability of the data. It is a transformation of a totally chaotic set of the data into something that starts to make sense to us. While we are going to discuss this matter next time, we need to understand before proceeding an absolute basic of probability distribution. A probability distribution assigns a probability to each measurable subset of the possible outcomes of a procedure. Normal or Gaussian distribution is a very common continuous probability distribution. It is a simplification, but it has been developed so we can start handling that matter of organizing the data in some simple and doable fashion. Continuous probability distribution is a probability distribution that has a PDF, and that has nothing to do with Adobe Acrobat program. PDF is a probability density function, or density in short, of a continuous random variable. Is a function that describes the relative likelihood of the variable to take on a given value. There are many types of probability distribution. There are myriads of them actually. And this is depicted on this extremely convoluted graphics here. There are zillions of them and they have exotic names. However, most of them are related to each other and ultimately to the normal. And that brings us to the exploratory data analysis, a very important part of the process, critical in fact. The goal of exploratory data analysis is to reduce the information contained in the data set to few key indicators. Now we've done already the initial data analysis and the data set is not so chaotic, but we would like to have as brief as possible description of it. How would we approach it? Well, we approach it by summarization of the data with visual methods to reveal trends and patterns. And those methods depend on the type of the data at hand. While there are many methods, those can be divided into 3 categories. And it's very important to understand that those categories, even though all of them are part of EDA, are not equal in the terms of understanding them and approaching them. Those categories are tabular, where data are being presented in forms of tables; numerical, when then one number or a set of numbers as specific indices are used to describe the patterns and characteristics of the data. And finally, there are graphical methods in which charts of graphs are used to describe the data. And very important thing here is that while tabular and graphical methods of presentation are intuitive and can be understood with ease in most cases, even with a person who has never heard anything about statistics, numerical methods of representation are hermetic, arcane, and can be very obscure and impossible to understand without careful study. And maybe it is the reason that sometimes, if the researchers don't want to give much of what they've done, they prefer to use numerical data over tabular and graphical. On the other hand, sometimes there's simply no place in the limited business analysis or in the limited by size paper to show the extended tables and graphs in the future process, so the numerical data are inserted. However, the knowledge of numerical methods of EDA are critical because those can tell us about quality and about how carefully and how methodologically correct or not the sample has been taken and how the study was performed. So, practical significance of EDA methods really go beyond just research. The EDA methods to be presented in this section are important not just for researchers. Any reader of scientific literature or business statistical analysis will encounter discuss here methods. And familiarity with those terms and concepts are essential for one's ability to critically appraise any statistics-based document. And this is particularly important for the numerical methods because, as I said, those methods are not counterintuitive, are not intuitive, they are counterintuitive, and they require the knowledge of specific concepts that cannot be inferred. Let us start with a relatively easy matter, with exploratory data analysis using tabular methods. Tabular methods use a different type of tables, and the most frequent are a frequency table and a cross table. Let's talk about the frequency table first. In order to understand what frequency table shows, we have to understand frequency distribution. It is an organization of the raw data in the tabular form using classes and frequencies. Frequency, the numbers of time a value occurs in the set. Relative frequency is a frequency counts expressed as percentages of a total observation. Cumulative frequency is a sum of frequencies for all values at or below given value. And cumulative relative frequency is the sum of the relative frequencies for all values or at below a given value. So, how to put all this theory into work? Well, frequencies table are useful for categorical data. Frequency table present the distribution of values by showing their frequencies, as shown in the example here on the left. Let's consider a study when we have 25 blood donors, and we would like to see how their blood types are distributed. So when we just put it in the data set, it looks totally chaotic. But when we put it in the form of a table presenting class in one column, followed by the frequency, relative frequency, cumulative frequency, and relative cumulative frequency, it says us much more. I mean, clearly it looks that type B and O appear to occur more frequently and with virtually the same frequency, while type A and B are not as frequent, but they are close to each other. That tells us more about the population than just looking at the random numbers. Contingency table or cross table is used to analyze the relationship between many categorical variables, as shown in an example here. Let's consider 100 individuals who are randomly sampled from a population as a part of study of sex differences in the handedness. So again, if we'll have a data set, it will be totally impossible to infer anything. However, when we put in this nice table, we can see that, well, clearly there's some, but not as big difference between males and females in terms of right or left-handedness. As I stated, for most people, tables are not a problem. Just looking at those, even if one don't understand the issue of frequency, one can infer what they present. But numerical methods are different. And this is the reason that I presented on this picture the numerical methods as present on the scroll are mostly taken from the Hermetic Arcanum, because that's what it is. Numerical methods include, but are not limited to, quantiles and quartiles, to the location measurements that are commonly known, such as median, mean, mode. Numerical ED methods includes also spread or dispersion measurements that include range, commonly known and understood, interquantile range, variance, which is believed to be understood, but it's usually very confusing for most, standard deviation, same as with variance, very frequently used, but few really understand what it entails, and coefficient of variation. Other methods include skewness, which is usually measured by using coefficient of skewness, kurtosis, measured by coefficient of kurtosis, covariance, correlation, and correlation coefficients. The most two commonly used are Pearson's correlation coefficient and Spearman's rank correlation coefficient. Quantiles. Bread and butter of statistics, especially for epidemiological studies. And here comes a problem, because I have encountered so many students and bright students and even interns and residents who have no clue what quantiles are, or worse, they believe that they know what quantiles are and they have actually no clue. And I blame the formal definition of quantiles for it. It is presented here on the bottom part of the screen. I'm not going to even to read it, but it induces the reaction as shown here in most of the medical trainees. But there is a simple definition of quantiles. Quantiles are points taken at regular intervals that divide the data sets into equal subsets. To discuss it more, quantiles are the data values that is a cutoff points. I emphasize points, not ranges, points. Marking boundaries between subsets. Certain quantiles have their own names, and here are the examples. Second quartiles are median. Fourth, quartiles. Fifth, quantiles. And hundredths, percentiles, and we're all familiar with percentiles from the pediatric growth chart. Now, the common misconception is the use of the name of quantiles to denote the subset they mark. Those subsets should be actually called properly thirds, quarters, fifths, and so on. Which brings us to the favorite terms of epidemiologists, which are quartiles. Quartiles are 3 points that divide the data sets into 4 equal groups, each comprising a quarter of the data, as shown in the left upper corner of this slide. Again, quartiles are points, not the ranges. A quartile is obviously a type of quantile. Their names are Q1, Q2, Q3, or Q1 is also called a lower quartile. They divide the first quarter of the data, therefore 25th percentile. They split lowest 25% of the data. Q2, second quartile or median quartile, 50th percentile. They cut off the data set in half. Q3, third upper quartile, represents 75 percentile. They split highest 25 of the data. Interquartile range, or IQR, is the difference between the upper and lower quartiles. So translating this into the practice, with the emphasis that quartiles are points, is shown on this little picture here. We have a data set, and in this data set, Q1 is obviously 4, Q3 is 8, and Q2, the median of the set, is 5. Obviously, we have rarely a situation, and this all is true. So in a little more complex data sets, as depicted here, Q1 will be 3, Q3 will be 7. However, there is no physical Q2. In this case, Q2 is 5.2, and in abstract, a number which exists between 5 and 6. Let's have a look on quartiles in even more complex data set, which is still very simple. So in this data set, as organized, Q1 is 64, Q2 or median is 71, again the not existing abstract number that is in imaginary existence between 70 and 72 data points. Q3 is 77, obviously, and to calculate interquartile range, one has to subtract 77, so one has to subtract 64 from 77. Now, the location measurements. Location measurements are very useful, and they could be one number in a simple status that pretty much tells us almost everything about population. The location measurements measure central tendency. The concept here is to finding the position of the value in the data set that best characterizes it. And those are very frequently and commonly used. Median, value separating the higher half of data from the lower. In the data set presented, obviously it's 5. Mean is the sum of the n numbers divided by the n. And in this data set presented here, it will be 6.2 because this is a number of the data here is 5, and when you sum them up you can and divide, you come up with the number 6.2. Mode, the most frequent value in the data set, and for this particular data set here, the mode will be obviously 3, as this happens most frequently. Now, and this part gives us an opportunity to introduce another concept in statistics, concept of robustness, a basic concept. Mean is obviously affected by outliers, because outliers goes into the calculation formula and they will change the outcome. However, median is not, because there is really nothing to calculate. The median is almost taken out without looking much into the outliers. So in statistics we say that median exhibits robustness against outliers. And term robustness is being very frequently misunderstood by physicians. I mean, generally speaking, robustness means the ability to resist, but most physicians understand it as a physical power or strength, but not in statistics. Robust statistics is a statistics with a good performance for data drawn for a wide range of probability distribution which is not affected by outliers. So robustness in statistics means resistance to confusion. Another important aspect of numerical data analysis are spread or dispersion measures. Spread or dispersion measure the degree to which the observed values are concentrated around a location measure which we just discussed, one of them. In smaller spread, values are tightly clustered around the center, around the mean or median, as shown on the picture here. The measures of spread include, but are not limited to, range, interquartile range, variance, standard deviation, and coefficient of variation. Let's talk about ranges. The two commonly used is a simple range and the index that we have introduced before, interquartile range. Range is a simple difference between the sample maximum and the minimum. It's a simple method, but it is very sensitive to outliers because obviously outliers when present are going to change it. Interquartile range, less sensitive to outliers, is the difference between the upper and lower quartiles, as we recall. Variance, denoted as S squared or sigma squared, is a measure of how far a set of numbers is spread out. Again, most trainees think that they understand it perfectly, but frequently they don't. Variance is simply a way of telling us how far the number allocated from the mean. Formula is shown on the left. Those who are mathematically apt and those who are mathematical aficionados do not need any explanation because it's so ludicrously simple for them. However, those much more biologically inclined require explanation of this formula. Formula is, as a matter of fact, very simple. As we can see here, xy is each of values of data, and it is being used in concert with the mean. One subtracts value of the data from the mean in a repetitive fashion, squares this, and obtain in that way the variance value. Variance value is squared in order to be always positive. When variance is 0, 0, there is no variation. That could be very good if somebody is looking for the consistent methodology, but it could be horrible if someone is trying to measure or study the actual population. It means there's something went horribly wrong. Variance is small when the data are close to the mean, and it is perfect for physiological studies when we are trying to have a consistent methodology and not have much outliers. When variance is high, that means the data are far from mean, which again could be horrible for the physiological experimentator because it means that his methodology is not the best one. But it could be also very telling about the subset of population. It would tell us simply that the subset of population, also known as sample, is very diverse. Now, it always looks nice, but since the variance is expressed in squared units, it is difficult to interpret it intuitively because we are not dealing with square units, not being mathematicians full time. And therefore, standard deviation has been developed and used, which is, not surprisingly, a square root of a variance. It showed the extent of variation from the mean naturally. The equation and formula is presented on the left side, and it's not surprising, simply a squared root of a variance. Small standard deviation indicates the data are close to mean, similarly to the previous case. high standard deviation data are far from means with the same connotation that I have discussed. Both variance and standard deviation depends unfortunately on the unit in which variable is measured, so it can be misleading when one tries to compare variables using different units. And that is being remedied by utilization of coefficient. And I found that, again, most medical trainees and even advanced research trainees use word coefficient having no clue what that word means. And therefore, I introduce it, and I apologize for those of you who are mathematical aficionados and know it all. Coefficient came from Latin word co, together, and efficere, to effect. In mathematics, number or other known factor of symbol by which another number or factor is multiplied is called coefficient. So as shown on the little graph on the left, or in the example here in the equation, a times squared x plus b times x plus c equals 0, a is a coefficient of x squared and b is a coefficient of x. In statistics this is true. However, in statistics, coefficient is specifically a measure of specified characteristic or phenomenon. After this explanation, we are finally arriving to the coefficient of variation. It is a ratio of standard deviation to the mean. And you see, we are applying opposite thing here. The coefficient is something that you are multiplying by, so in order to know the coefficient, then you shall divide. Relative standard deviation is a coefficient of variation expressed as percentage. The formula is shown on the left. Again, it's very simple. The meaning of the number when one sees it in a statistical analysis, being it paper or business document. Coefficient of variation lower than 1 indicates low variance. If it's equal to 0, perfect, no variance happen. That could be excellent if we are dealing with a medical clinical laboratory performing a test on the same sample. Right? Rarely happen, but that would be ideal. Coefficient of variation more than 1 indicates high variance, a disaster for said laboratory. But in the epidemiological study, simply indication that we are dealing with a very diverse population. As we discussed, coefficient of variation is superior to variance because it has no units. So it can be used for comparing dispersion of variables measured in different units. Now, skewness of kurtosis is a thing that one will not come across very frequently unless one is dealing with epidemiological studies. But some physiological studies included this as well. Skewness is defined as a deviation from symmetry with respect to location measure. It is a unit-free index. A formula is shown on the left. And again, what we are dealing here is a similar concept for those who are not mathematically apt. We have a data value, and we're subtracting from it. We are subtracting mean from it, and we're dividing it through a standard deviation, the sum of these many things. Skewness is denoted very frequently by a symbol B1. If B1 equals 0, if we'll see this in medical paper or in business analysis, that means that the variable is distributed symmetrically around X, around the mean, the location measure. The both tails of a distribution are symmetric. And you see, this is a tricky part. This is a numerical index. However, it represents the graphics. So this is one of the arcane method of using the actual number to represent graphs. And every statistician see it immediately in their minds, but most of us physicians don't. When B1 is larger than 0, we are dealing with a positively or right skewed data set. As depicted on the picture here in blue, there is a longer tail for values larger than the mean. If skewness is negative, we are dealing with left skewed or negative data set, negatively skewed data sets. That means, as depicted here, that the tail is longer for values that are less than median. And it has implication, especially when thinking about the population. A wonderful coefficient, a coefficient of kurtosis, which kurtosis is a measure of pickedness, how high or how long a pick is. So the coefficient of kurtosis, denoted as B2, is the degree of pickedness of a distribution as compared to the normal Gaussian distribution that we discussed. It is usually unit free. The symbol is shown here, and this is again similar concept but a little more simplified, because we are really not interested in tails here. We are interested in the peaks, and peaks are the maxima of values, and hence we actually subtracting mean in this formula from the value of the data in a summation fashion, and we are then divided it by the type of transform standard deviation. So, the numbers which we'll see in the paper denoted by B2, and that should automatically induce in our mind the vision of a curve, are leptocortic when B2 is more than 3. That means that the distribution is picked more than normal. B2 equal 3 should bring us to the mind the mesocortic curve. It means that it is picked as normal, and when B2 is equal than 3, then the curve is platycortic. That means it's picked less than normal. And while you may not come across all these things, this coefficient of kurtosis indicates how really well versed one has to be in those terms, because you really have to know the free value here, otherwise usually no explanation is given. And some researchers can get away with doing some not so savory stuff just by simply presenting coefficient of kurtosis and getting away with the things they would like to get away. Or sometimes people simply overlook things. Now let's move to another important basic concepts which are related to each other. Those are covariance, dependence, and correlation. They're extremely important matters for physicians and for medical sciences. Covariance is a measure of how much two random variables changes together. Dependence is any statistical relationship between two random variables. Correlation refers to statistical relationship involving dependence. And here the most important sentence that we are all taught and then we'll tend to forget and then we'll take to make a most common error in thinking, naturally very frequently, because this is the way how human thinks. For most human beings, correlation would apply causation, but obviously it does not apply causation. One who thinks that correlation applies causation, that means that because two things correlate with each other, then they have to be involved in the cause and effect relationship. The person who thinks it is wrong, because it is possible, but it may be not as well. The post hoc ergo propter hoc fallacy, that means that if something happened after something, that thing has to be caused by the things that happened before, is extremely dangerous in medicine, because it can lead us to believe that certain manipulation or lack of manipulation result in the certain outcomes, when in fact there is a simple coincidence. Let's start discussing covariance. Covariance measures association between two numerical variables. Again, we'll see formula here on the left. May appear to be sophisticated to those who are mathematically not apt, but in fact it is simply very straightforward way of doing things. We are having actual observations from which we subtract the mean. We're multiplying this, and by that process in summation we can establish the covariance between those two variables. The interpretation of the data that you may find in the scientific literature on business analysis is as follows. Covariance xy when equal 0, it indicates that two variables are independent. They simply do not correspond to each other. They change without any dependence. If covariance is more than 0, positive, then obviously x and y variables are positively associated. So the greater value of x corresponds with greater y's. If covariance is negative, then there is a negative association between x and y. The greater values of x correspond with smaller y's. So the sign plus and minus of covariance show the type of linear relationship where linear is a key between x and y. However, the magnitude of covariance is hard to interpret just because of the way it is calculated as it is showed on the formula here. Therefore, we need to normalize it. And that brings us to a correlation coefficient. We discussed what coefficient is, but we need to have a look on the basic statistical terms of normalization, what it is. Normalization is a creation of scaled version of statistics to allow the comparison with elimination of any influence. And I depicted it in a very simplified graph on the left side. We see three very different shapes, and we apply the procedure that make them standardized. Now, many things are lost, it's true, but it still allows us to compare those two different shapes and sizes using that type of instrument. So correlation coefficients are normalized versions of covariance. Correlation coefficients measure the degree of correlation. There are numerous correlation coefficients. Most commonly used, especially in biological sciences, are Pearson correlation coefficients and Spearman rank correlation coefficient. But let me emphasize one thing. While there are many of those correlation coefficients, for most medical studies, and I would argue that for most business analysis, those two correlation coefficients should suffice. If there is attempt of doing any more sophisticated analysis, there's likely something not right here. But let's start our discussion with presenting the most common correlation coefficient, denoted as R and known as a Pearson product moment correlation coefficient, or simply Pearson in the jargon. It is a measure of the linear correlation between variables x and y. What is linear? Again, for those mathematically not apt. Linear xy relationship is modeled best by the straight line. So whenever there's a relationship that can be modeled by the simple straight line, it is a linear relationship. The formula is shown on the left, and again, it is simply we are taking our curve xy and dividing it by the standard deviation multiplied by each other for x and y respectively. Therefore, one can deduct that if we'll see our value in the paper and it is 0, well, there is no correlation, and that's good if the author would like to prove that, then he achieved his goal. But usually it is applied to show some type of correlation. So if R is equal -1, there is a total negative correlation. If R is equal +1, it's a total positive correlation. We usually do not see those ideal values, but we see something in between. So whenever we have a paper or business analysis that purports that there is a correlation between two variables, we should look into the text to see if the R there has been reported, and if it's between 0 and 1 for total positive and between 0 and -1 for total negative. Pearson removes the dependence on the unit by scaling the correlation by the product of standard deviation of x and y, which is very nice and it's very useful, but unfortunately it is not robust. Remember the term robustness. It's not robust to outliers, unequal variances, non-normality, that is when the population distribution is not normal, and non-linearity. So we need something else. And in order to understand how the something else, called the Spearman's rank correlation coefficient, was developed, we need to talk a bit about ranking. A very simple concept, but it's being confused totally because it is, in my humble opinion, not very intuitive for physicians. Now, obviously, rank is a relative position in a graded group. Let's see here, we see an Olympic pedestal, and the athletes are being ranked, put on the different places on the pedestal depending upon their numbers and score, the value they achieved during the athletic performance. So the ranking, analogically, is a transformation of data in which values are replaced by the rank. The comparison here is that instead of remembering the name of athletes or their scores they achieve in their sport achievement, we are simply calling them first place, second place, third place, not Mr. Smith of score 27, let's say, having second place, but just we're calling them by their rank, number 2. So the ranking of a numerical data set is presented over here by the same analogy, except that our pedestals number is increasing, and of course for the big data set will be very huge. So we have our quote-unquote athletes with their score or numbers values which are assigned to a different ranks, which can be presented in the table as shown here as well. So that's ranking. And ranking is important to understand as Spearman rank correlation coefficient. It is a measure of this time not linear but monotonic dependence between variables x and y, because clearly not all dependence will be linear. So the best model available to describe those nonlinear variances will be monotonic dependence, and what it is. In monotonic relationship, y moves in one direction, either up or down, as x moves, but that relationship is not necessarily linear. And Spearman rank correlation coefficient calculation formula is presented over here, while it appears to be confusing by those not mathematically very apt. It is actually very simple. Spearman or rho is calculated by applying the Pearson's correlation coefficient formula to the ranks of the data, not to the values. So it's as if we would replace the name of the athletes or their scores by their numbers on the pedestals. Spearman's reflects monotone trend between variable x and y. When rho is +1, we have a perfectly increasing monotonous trend. For the Pearson or rho, from 1 to 0, there is increasing monotone trend. So, translating this to English, when y is increasing, when y is increasing when x is increasing. Spearman's equals 0 means that there is no monotrend whatsoever present between two variables. For experiments between -1 and 0, there is a decreasing monotone trend. When X is increasing, Y is decreasing. And when ρ, theoretically, because in practice it's very unlikely to ever happen, we have a perfect decreasing monotonous trend. Spearman rank correlation coefficient is robust to outliers, robust to inequal variances, non-normality and non-linearity. On one hand, it is therefore an advantage and a good index. But practically speaking, and this is a little secret I have learned from my mentor, whenever you see in a simple epidemiological or a simple clinical study a Spearman ranks correlation coefficient being used to show a relationship, likely something is off. Likely the number of outliers is big. And I'm not saying that this is indicating always some type of a nefarious manipulation. But in most cases, Spearman rank correlation is unusual when used in a simple physiological study. Spearman rank correlation is also non-parametric, as exact sampling distribution can be obtained without parameters of a joint probability distribution of X and Y. So it is a good way of going with non-parametric analysis. And this concludes the part 1 of this presentation. Let me just make a conclusion for the part 1 of this lecture. Statistics is an essential component of both science and business of medicine. Despite this fact, statistical illiteracy and innumeracy is prevalent among physicians. This situation should be remedied. Study of statistics poses many challenges, but those are well worth of overcoming. Statistics is based on definite numbers of principles. It is best studied in an incremental fashion. Statistics reflects act of interpretation, not irrefutable facts. It can be and is misused and abused. Statistical analysis are results of a multiphasic process that starts at sample selection and ends with presentation of conclusions. Appraisal of statistical analysis requires familiarity with all phases and especially with numerical methods. Understanding of tabular, numerical, and graphical methods of EDA is critical for assessing the quality of statistical analysis. And this subject shall continue. I would like to acknowledge at this moment the help of my mentor, Dr. Stephen DeCherney, who is a professor of business statistics at UNC School of Business, as well as a professor of medicine at UNC School of Medicine. I have no conflict of interest to disclose, and the floor is now open for questions and comments.
Okay, thank you very much, Dr. Borg, for that wonderful presentation this evening. And I'm going to have a few announcements here, but while I'm making the announcements, if you have a question, if you'd like to raise your hand, we'll get to you, or you can type your question into the Q&A box at the bottom of your control panel. And I'm also going to go ahead and give you the link to go fill out the post-presentation evaluation. I'm going to put that in the chat box here. You'll also get an email from us in the next 15 minutes or so with that link, as well as a reminder about next week's presentation, which we hope you all will join us at. And there have been a few questions about whether we will have the slides available, and the answer is yes. We'll follow up with an email to you with a link to those slides. And also, we will have a video of this presentation available for you to review. If you want to watch it again before next week, we'll get you a link via email about how you can watch it and review it, because there was a lot of excellent information in here, and I know I certainly need to, there are parts that I need to review again. So it looks like we're getting some people saying thank you in the chat room. I don't see any raised hands. So we'll just give it maybe a few more moments here if anyone would like to raise a hand and ask a question or type a question in. Okay, here we have a question, and Dr. Borg, the question is Spearman coefficient sometimes the most appropriate measure?
Yes, it is. Depending, as I have stated during the lecture, statistics can be the biggest lie ever, or it can be the biggest truth available. The whole tricky part in applying statistics is precisely trying to feed the formula, but not to obfuscate, not to confuse, but to present the most clear conclusion. And there are many, actually, correlation coefficients. Simply in biological sciences, Pearson appears to be most used with models which are established and maybe in some extent obsolete. So by this, the Spearman's correlation coefficient, when dealing with the real world, when we are not dealing with a tissue culture when we can control, when we are not dealing with laboratory experiments using laboratory animals and batch manipulation, absolutely it can be. What I'm trying to emphasize here, that not a single statistical method is right or wrong. It all depends upon circumstances.
Okay, we have another question here, and it's, Dr. Borg, do you have any recommended books for medical statistics?
We'll talk about this. This is difficult for me to endorse anything. There is one book I mentioned. I'm going to give a list with comments during the second lecture, because I think it's much more appropriate. However, one of available textbook is Kirkwood's Essential Medical Statistics. It is written, it has been published in 2004, and I believe there is a new edition. It can be a starting text. However, let me tell you one thing. The best way of studying statistics is actually to study a text which are hypertext based. That means that you have links within a text that you can just click on it and go to definition. It is extremely difficult to a physician to have a paper-based textbook and study the statistical terms. It may be overwhelming. And there is a plethora. If you go to your iPad, if you go to your Android tablet and just enter the statistics, there are a few very good Android or iPhone-based texts that could be a starting point. But again, I will give those references in details during the next lecture.
Okay, it looks like we've answered the questions we've received, and so I just would like to once again thank our presenter, Dr. Borg. Thank you very much, and thank our attendees for joining us tonight. And we hope you'll again join us next week, and look for a follow-up email from us in the next 15 minutes or so. And with that, we'll say good night. Thank you very much.
Thank you very much. Have a good night.